it turns out that if you study the field of this method, before the conjugate gradient method came into existence, its ancestor was a similarly named method called the conjugate directions method. Okay, these p vectors, they look like conjugate directions, right? So just starting on the basis of this, the method that people invented was the conjugate direction method, and we will see it ran into some problems, essentially computational problems. And what solved it was the conjugate gradient method. So we need to first understand the conjugate directions method, right? So, so the conjugate directions method. Also short form CDM. Let's put in bracket ancestor. Okay. Now, what we have been, as I mentioned, given Ax equal to B, I don't want to solve the system of equations directly. If I don't want to solve something directly, what is my option? What is my alternative? Something that is not direct is called what? Well, obviously indirect, but something else. If I don't get the solution in one shot, what do I call that method? Iterative method, right? Was our gradient descent an iterative method? Yes, because I took discrete steps, each step I kept getting better, right? So this CDM is also an iterative method, okay? So it is iterative. And guess what? I can write the iteration the same way that I wrote the iteration for a line search method. So I want this. And the very interesting thing is that this pk, I am not going to insist on it being a descent direction, because then I am back to a gradient descent. So I am going to say need not be a descent direction. But just as we know that there is no free lunch, there are some different constraints that I need to impose on this p. Okay, so let's put a however. No points for guessing the first requirement. What is it? The p's that I choose should be conjugate with respect to a. Pi's must be okay. The second step, the second requirement rather, can also be guessed by you with a little bit of maybe a few hints. So when we did, as you did in the tutorial also, when we have a quadratic cost function, was it possible to find out the exact step length? Was there in fact a closed form expression for the step length? Yes. Is my cost function here quadratic? It is. So does it make sense for me at all to do line search? There's no sense, right? I'm wasting resources in doing line search when I know what the exact line step length should be. So the second requirement is that all the alphas are exact step lengths, exact minimizers of the cost function along which direction? If I'm at the kth step, right, and I want to reach xk plus 1, what direction am I going along? Pk, right? If I'm at k and I want to go to k plus 1, I have to go in the direction pk and a length alpha k. And because my cost function is quadratic, I can do simple calculus, find the exact step length required to reach there. So I can get a closed form expression for alpha k. And it's common sense to use exact when exact is available, right? So that's the simple, you can call it a requirement, it's more like common sense. Obviously you should use the exact step length, right? So step length is an exact minimizer of phi x along the pk direction. Okay. In other words, again this is question. Okay. This is kind of calculus review. What should I write over here? I am at the kth step. So what is my variable? Alpha. Pk supposing has been given to me. Pk has come from step 1 or requirement 1, right? So alpha pk, and I am going to set this equal to 0. The alpha which solves this is going to be given the name alpha k. That's how we do it, right? In fact, this alpha k has a very nice closed form expression, as was there in the tutorial also. I'm going to write it over here. And remember, Rk was nothing but, Rk was the residual defined as Axk minus b. Okay. So I started with this whole business of conjugacy, and based on that I said, okay, let me try to discover a iterative method. So what are the nuts and bolts I started putting together? I said, okay, give me the directions in which I walk will be the p's, all right. And since I'm walking along the p's, I have the exact minimizer. Okay, I get the alphas. Now, what is really surprising, and it's not obvious looking at this, that with these two simple requirements, here is, if you do this, I'll tell you what happens. You are guaranteed convergence of the problem in n steps. That was not possible for you in gradient descent. In gradient descent, we saw that graph, right? Depending on the condition number of A, you took more than the size of the matrix, those many steps, right? But here, this is a guarantee over here. Okay, so let's write this down. Starting from, let's say, x0, then we have the sequence xk generated as per 1 and 2 above, okay, converges to the stationary point in at most n steps. Right? It's so simple looking, it's so elegant, and all I had to do was to start by introducing just one new generalization of the idea of orthogonality into conjugacy. Any questions on the statement? The statement is clear. If you generate step vectors like this, I have not told you how to generate the p's. That's the hint that the devil lies in those details, right? And you get the, if I give you the p's, for example, do you think alpha k is complicated or difficult to compute? Look at the expression for alpha k. It's just matrix vector product, right? It's going to take no time in MATLAB, for example, for you to evaluate this. And you're done in n steps. Okay. In fact, as I said, the devil lies in the details. That's where the CDM got stuck in terms of implementation. The cost for generating the p's became very high, but we'll get to that. Okay. Now, obviously, I've written an extremely strong statement over here, and we would want to see a proof. Right? Why is it that it converges in at most n steps? That means what? It could also be lesser. So let's look at the proof. Is everyone with me? Okay. So let us say I am at some in between kth step. Okay, so we are at step k. Obviously, I am going to assume k is less than n. That's a common sense assumption. Assume k is less than n, less than equal to n. Now, if I have reached k, how many, well, nothing to do with k, but if I have n as the size of the matrix A, how many conjugate, how many linearly independent vectors are possible in n dimensions? N and no more, right? So that means how many p's do I have? I have n, right? So I have p0 up to up to p n minus 1. This is my set of conjugate directions. And moreover, as we showed, they are linearly independent. Okay. So if I know that they are linearly independent, okay, I want to know that how far am I starting point to end point. So if I write a vector like this, so x star is where I end, x naught is where I began. Okay. In this case, is this a vector? Can it be written in the basis of p's? Very obviously yes. So I can write this as summation sigma I pi. This is just basic linear algebra, basis expansion, I equal to 0 to n minus 1. Okay. Again, we have one tool, one trick in our box. If I want to evaluate the sigmas, what can I do? What is the tool that I have used and will continue to use again and again? Use the conjugacy property, right? If I stick a pk transpose pk, sorry, if I stick a and a pk, right, it will annihilate all terms but what? Only one term will survive, right? There are p0 up to pn minus 1. If I do this trick of pk transpose A, only one guy that's going to survive, all other terms are going to go to 0. So if left multiply by, I'm going to take x, sorry, not x, pk transpose A on both sides of this expression. What am I going to get? Pk transpose A x star minus x0. What is going to be left on the right hand side? Who survives this sigma k, right? Sigma k is the only guy that survives this. Okay. By the way, is this useful? Is this a useful way of calculating sigma k? Common sense answer. Is this a useful way of calculating sigma k? Look at the expression. Is it useful? No, because I don't know x star. No, I do. If I knew the solution, why should I do all this? This is just a way of manipulating the expression. I obviously don't know x star, so I cannot evaluate sigma k this way. Okay. One mistake over here, which is what? There's something missing in this expression. I forgot to write pk transpose A pk. So the expression I got for sigma k was pk transpose A x star minus x0 pk transpose A pk. Okay. Now I notice there's a x star minus x naught over here, right? This is telling me how far am I from starting to end point. But I want to somehow, what is the kind of interesting guy missing from this expression? xk is not there. Where I am at the kth step is missing. So let's try to bring that guy into this expression. xk was, if I started with x0, how do I get x1? x1 was x0 plus alpha 0 p0. I got my x1. To that I would add alpha 1 p1 and then alpha 2 p2 and so on to get to the next thing, right? So if I write this in a clever way, I can write this as alpha 0 p0. This gave me x1. To this I would add what to get x2? Alpha 1 p1, alpha 1 p1. So this became x2. right? So dot dot dot. What is the last term that should come? Alpha k or k minus 1? K minus 1, right? Pk minus 1. So notice one very simple thing from here. If I take xk minus x naught from here, what am I getting? Alpha I pi, I going from where to where? 0 to k minus 1, right? So this distance, notice what has happened over here. This distance xk minus the starting point is now written as a linear combination of the p's, but not all the p's. Look at the upper end of the summation. How many p's are coming in here? Only k minus 1 p's, right? That's giving us a hint. Okay. So okay. Having gotten this expression, let's apply our usual trick. What is our usual trick? To kind of decimate this. See, I don't know these alpha. I don't know. Do I know these alpha i's, for example? I do know these alpha i's, right? That was given in the recipe of the CDM. Alpha i's were given by exact line search, right? So I can also estimate the alpha i's by using the conjugacy property, right? If I stick a Pj transpose A over here, it's going to isolate one of the alphas. I'll get something to compare with. Okay, so let's quickly do that. I am going to take let's take Pk transpose A multiplied by xk minus x0. What will I get? Will I get alpha k? There is no Pk left on the right hand side. So therefore, this is going to be equal to 0. Okay. Now, here is the final trick. So this, remember this expression for sigma k over here. So what I am going to do is, okay, let me just copy it from here. So sigma k is Pk transpose A. Sigma k is equal to Pk transpose A x star minus x0. What was the denominator? Pk transpose A Pk. Pk transpose A Pk. I am simply going to add and subtract xk. Fine. I just added and subtracted xk. Can I use the previous result anywhere? Right? This guy is sitting over here. Pk transpose A xk minus x naught. That means when this guy acts on this guy, I'm going to get a big fat 0. So this is going to be Pk transpose A x star minus xk divided by Pk transpose A Pk. Fine. Looks tedious, we are going on and on, but this is actually the final step, because what is A into x star? B, right? So I can write this as Pk transpose, this is B. What is A into xk? I'll leave it like this. Pk transpose A Pk. Does this what is B minus Ax or Ax minus B? Minus of the residue. Residue was Ax minus B. So this is nothing but minus Rk, right? Ax minus B was R. So this became minus Pk transpose Rk divided by Pk transpose Apk. Does this expression look familiar? We have seen it before. What was it? Alpha k. Okay. So do you see what has happened now? I have my final, the distance between my starting point and my end point is written as a linear combination of all of these vectors from P0 to Pn minus 1, and the coefficient sigma are nothing but the step length I took at each iteration. I did first iteration x0 plus alpha 0 p0, right. So, at each iteration I am going along that conjugate direction a certain length, right, and at the end of it in n steps I will reach the solution. Okay. So, subsequently we will do a lot of visualization on this to really convince ourselves that this is done. Okay. So, this we'll just review the proof. What did we start with? Set of linearly independent directions. That means the start minus end, the error should be written as a linear combination, and it turned out that that linear combination is built in the construction of the method itself. The sigmas were the same as the alphas. That means this distance, it has to be a vector in n dimensions, it is covered. So, in each step I walk along that t and that length alpha, in the end there is nothing left, there is nothing left. And I think this is, where is that expression gone? Yeah, this is a very nice way of looking at it. Okay. So, this is the proof that guarantees to us that at most, so where does at most n come from? Is it possible for me to reach sooner? If, how can the sigmas be 0 or the alphas? What? So, pk transpose a pk, that cannot be 0. What am I left with? What is the term that can go to 0 soon? Rk or grad fk, right, basically. So, the moment you reach Rk or grad fk equal to 0, depends on the, once you reach, yeah, so you can reach a stationary point sooner also, right. And so that's where the at most n comes from. Okay. So, this is not the last time you are going to see this, we are going to work with this a lot. We will, next what we will do is we will try to visualize this in geometry, so that the algebra gets a little bit more settled inside. Okay. Alright, so okay, so we have covered a fair amount of ground today. We had this just a starting discussion on symmetry. Is it really needed? We found out that it's not really needed. If it's there, it's no problem. It doesn't survive the quadratic form. Then what did we do? We figured out how to write Ax equal to b in the language of optimization in a clever way, right? In a way that would give us faster convergence and more accurate answer, right? And then we introduced one new, after visualizing them, we introduced a new property of conjugacy with respect to a positive definite matrix. And this simple property gave us all sorts of lovely properties. For example, they are linearly independent, and if you follow this simple method or recipe, you can think of it, that you work with these conjugate directions, do exact step length, you reach a solution in n steps. Okay. So, this is very powerful. If you are able to get this to work and you do not have enough memory on your machine to store the matrix A, leave alone compute A inverse, here is a way by which you get this answer in n steps. Okay. Notice that the only thing I need for this is this expression and the p's, of course. Give me the p's, give me this. Notice over here, do I need to explicitly store the matrix A? This is a point that those of you who are doing numerical work will appreciate more. I never ever need A in isolation. Like if I write A inverse, then I need A in isolation. This expression only requires the product of a matrix with a vector. A never appears in isolation. A appears as a product with pk. So, in numerical routines, that is a much relaxed requirement, to not want A, because if I want A, I need to store it in memory, I may not have enough memory. But A into a vector is actually n entries, right? A times a vector is n entries. A by itself is n squared entries. Huge difference in memory, right? So, there are very clever routines which will work just with matrix vector products. So, if I am able to do matrix vector products, this expression is fully made of matrix vector products and vector products. So that's why iterative method is specifically designed for places where you run out of memory and you cannot do the whole thing directly. It will take more time than a direct method, but you have no option. Okay. So those of you using commercial software for solving systems, if you see the log, it will say using this indirect solver or that indirect solver. This is what is one of the methods in between. Okay. Any questions on this? Okay, I'll stick around for a few more minutes. If you have any. By Gaussian method, Gaussian elimination. Gauss elimination also has complexity n cube, right? And it's also a direct method. So if you have enough memory on your machine, it's preferable to go for a direct method. It is fast. If you don't, then you cannot do Gaussian elimination also. Gaussian elimination and its cousin is LU decomposition. Same complexity, same thing. So when I say direct, I am referring to both of them. The other trick, other extra flexibility which a iterative method gives you, which the direct method does not give you. In a direct method, you get the final answer in one shot. In an iterative method, you may decide beforehand that I don't want 10 to the minus 16 error. I'm okay with 10 to the minus 4 error. That means I can abort my calculation earlier if I'm okay with a less accurate result. But I have no such flexibility with a direct method, right? I have to wait for the whole thing to come. So this is why in many big data science applications, iterative method is preferred, because if you get a good enough, error to begin with after several iterations, you can stop. In fact, if you remember the log that we had seen of the error of gradient descent, it was a L-shaped graph, right? Most of the progress was made in the first several iterations, and then it was very slow progress. So many strategies are just run it for a few iterations, get the error low, and then switch to something else. Okay, so that flexibility opens up with the iterative method. I think those of you who are doing ML would be familiar with this.